minus 2. 2 minus 2 is equal to 0. Oh, so I start first from S3, S2, S1, S0. So I'll replace this with as now a small positive, because I want to get this. So 2 epsilon minus 2 over epsilon. No. To get this, I'll multiply this times 0 and this times 0, which is a 0. Okay. This, we don't expect a term here because of the pattern. So this may not be the best example. Because we expected a 0 and some non-zeros. This has given us a 0 and a 0, but we expect a 0 and some non-zeros. This should not have been a 0. So this is not the best example. Probably at a later date, as I update the notes, if I get a good example, I will add onto the notes. And finally, I've said we replace this with a small positive constant. So this becomes 2 epsilon minus 0 over epsilon. So it's 2 epsilon minus 0 over epsilon is equal to 2. So this epsilon is a small positive constant. So meaning positive, 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 positive. No sign change. So a 0 indicates either instability or marginal stability. For this case, S is equal to J, is S on the J omega axis. It means it oscillates without increasing or decreasing because it's on the J omega. S is equal to plus or minus J. They occur in conjugates. The second special case is you may have a row of all zeros. What happens? Once you have a row of all zeros, you have to define some auxiliary polynomial. Which is based on the row above the row with zeros. Now we have an example here, and it may not be the best example because first, the two conditions, Q of S, same sign. And the second condition, all coefficients exist. All coefficients. Must exist. Despite the fact that we know that this is unstable because of the negative sign, unstable. Because of the negative sign. But we just need to find the number of poles. Our question is number of poles. Poles on right hand side. So we'll proceed despite the fact that we know that it is unstable. we will just proceed with the process. So the first is this is 1, 2, 24, 48, 25, 50. The negative. So the first is right 1, 2, 24, 48, 25, 50. I say that we can as well, this is a negative, you can as well divide this, divide by 2. All this row to be 124, negative 25, and then 124, negative 25. With no loss of, the process will still continue properly. So 2 times 24 minus 48, so it becomes 48 minus 48 over 2, which is a 0. 2 times negative 25, 1 negative 50, so it becomes minus 50 minus negative 50 over 2. Minus 50 plus 50 is equal to a 0. So I also get a 0 here. So this is a row of all zeros. What happens? If you get a row of all zeros, then we go to the row above the all zeros. So you have 2, 48 minus 50. So you make a polynomial based on this row. This is s power 4. So it becomes 2s power 4 plus 48s squared. So this becomes 2s power 4 plus 48 reduced by s squared minus 50. And then, because this is the same polynomial as this, so you now get dp over ds is equals to 8s cubed plus 96s. Now this becomes a coefficient of s power 3. So I'll now replace my zeros with 8 and 96. So where I add zeros, I cancel the zeros and I replace this with 8 and 96. And then I proceed. So I've just replaced my zeros. It was 1, 2, negative 24, and this is negative 50. This is negative 50. Just allow me to read the notes. 32, 32, proceed S. Just allow me a minute, proceed S. So this should be negative 50. This should be negative 50. So these were our zeros. Now I can either divide through by whatever number, but for this example I didn't divide, so I can multiply that times that. This 48 times 8. 8 times 8, 64, 32, 38, 384, minus 2 times 96 is 192 over 8, which is equal to 24. Next is 8 times negative 50. 8 times negative 50 minus 400 minus 0 over 8, which is minus 50. Finally, (24) times 96. The next is 24 times 96 minus 8 times 50, which is now positive, over 24, is equal to 112. Which is this. And finally, negative 50. 112 times negative 50 over 112 is negative 50. Now we look at the first row and you say that there's only one sign change. Let's check some. Oh, let me check if there is one I have. Yeah. This is an old question. S power 6 plus 2s power 5. Can check this. S power 6. S power 6 plus 2s power 5 plus 812. (1616). No. 2016-16. Okay. S squared. So this 1, 2, 8, 12, 20, 16, 16. So I'll write 1, 2, 8, 12, 20, 16, 16. Now these I need somebody with a calculator. 16 minus 2, 4 over 2, this 2. 40 minus 16 over 2 is a 2. This becomes 16 here. Because 16, 2 times 16, which is 32 minus 0. The next is 32 minus 0 over 2, which is 16. Now come to the next row. 24 minus 4. 24 minus 4 over 2. 10. 32 minus 32. 32 minus, it's a 0. And finally, 20 minus that's 32 over 2. 32 minus 32. I'm sorry for that. First is 24 minus 2. 2, 8, 12, 20. 2, 8, 12, 20. Yeah. I think it's correct. 20. 24 minus 4 over 2 is 10. 32 minus 32 is a 0. And then finally 20 minus 0, 20 minus 0 over 10 is 2. And then 160 divided by 10 is 16. And finally 16 should come here. 20 minus 160. So 0 minus 160 over 2. This question is and then 32 minus 32, which is a 0. Okay. Next now is 20 minus 0 over 10, which is a 2. Then 160 minus 0 over 10 is a 16. Finally is 0 minus 160. 0 minus 160 over 2 should be 80. I think I'm missing something. I was expecting this question to have a row of zeros. A row of zeros. I may be wrong. I was looking for a question which has a row of zeros. Sample questions. It may not be there, so if I get it, I will look for an example. I will add an example that has zeros, a row of zeros in the notes. Now let's look at the application of root locus. Supposing you have a feedback system, which the gain is variable. The question is, can we increase gain indefinitely? This could be a system whose transfer function is 1 over all this polynomial. And now we have what we know as a proportional control, K, controller. So K is a controller. Proportional controller. At a later date, we are going to look at proportional, integral, PID. These are called PID controllers, proportional integral derivative controllers. So this is just an example of a proportional control. You have your system made of this transfer function, s squared plus s plus 1. Let me write it properly. S squared plus s plus 1 s plus 2. This is your system, 1 over. Now you introduce your proportional controller with just a proportional, it's gain. This gain just amplifies the error, because this is an error signal. This is R and this is C. This is feedback and this is E, and this is a controller. So what happens? We want to see, can we increase the gain indefinitely? Now, recall we close the loop by saying K G over 1 plus GH. So that 1 plus GH is the characteristic question. Is a characteristic question. So 1 plus GH. This GH is 1. 1 plus GH. 1 plus GH. H is 1 is equal to 1 plus K over S squared plus S plus 1 plus no, this S plus 2. If you cross multiply by, it's G over 1 plus GH, you cross multiply by this S squared plus S plus 1 S plus 2 plus K. It becomes your characteristic equation. Now, if you expand this, is S to the power 4 plus 3S squared plus, you can expand this, S cubed plus S squared plus S plus 2S squared plus 2S plus 2 times S, so it becomes, this is S cubed, so it becomes S power 4. There's an S outside here, plus 3S squared plus 3S cubed plus 3S squared plus 2S, now plus K, which is this. And when you equate to 0, you get the characteristic equation. Now, 1, 3, 3, 2, K. 1, 3, 3, 2, K. Now we do 9 minus 2 over 3. It becomes 7 over 3. 9 minus 2 over 3. 7 over 3. Now, the next is 3K minus 0. 3K minus 0 over 3, which is equal to K, which is this one here. Now, you should be able now to know the pattern. Whenever you're dealing with the, you should know the pattern, K, K, K. Finally is 14 over 3. This 14 over 3 minus 3K. 14 over 3 minus 3K over 7 over 3. You will multiply by 3, it becomes 14 minus 9K over 7, which is 14 over 7 minus 9 over 7K, which is equal to 2 minus 9 over 7K, which is this one here. And finally, if I multiply this minus 0 over this, I get K. Now, for the first column to be 1, 3, 7 over 3, 2 minus 9/7k and k. For stability, this must be positive. It is clear that k should be equal to 0, greater than 0, for it to be positive. The second one, 2 minus 9/7k must be positive. Or how do I put it? 2 should be greater than 9/7k. Or k, 2 times 14/9 should be greater than k. Or k should be less than 28/9. It's 28/9. No, 2 or 4. No, 2 times 7. I'm sorry. This is 2 times 7. 2 times 7. I've cross multiplied 7 and 14. Meaning k has an upper bound. For the first column to be positive. That is k should have 0 and k less than 14/7 over 9. 14/9. 14/9. Let me just make that correction. I will look for I wanted to make this correction 14/9. So k must have a lower value and should 14/9. So that's an application of root locus in feedback systems. In feedback systems, if you are doing the control by increasing the error by proportional controller P, where the error increases, the error is increased proportionately by a factor k. So ke has a maximum. The error times k has a maximum given by this. And I think this brings us to the end of root locus. No, sorry, root array, root stability. Which in summary, we saw that roots should lie on left hand side, or should have negative real parts. Alternatively, bounded input, bounded output, or response should die out. Go to 0. 0. When no input. Input is applied. And we say, instead of doing examining each root, we use root locus, root stability criteria. So now, the next topic is known as root locus. I think after the root locus, we are going to look at frequency response methods. Frequency response methods, and then controller design, and then we go to instrumentation. So probably after next week, we'll go to the second part known as instrumentation. Now, what's a root locus? Supposing you have your system K over S, first order system. First order system. With this, with a variable gain, say that closed loop transfer function G over 1 plus GH, which is equal to K over S 1 plus KS. If I multiply 2 by S, it becomes K over S plus K. Supposing K is equal to 1, it becomes 1 over S plus 1. Roots at S is equal to negative 1. For K, 2, it becomes 2 over S plus 2. Roots at S is equal to negative 2. For K is equal to 3, it becomes 3 over S plus 3. Root at S is equal to negative 3. Let's study. For K is equal to 0, it becomes 0 over S plus 0. Root at S is equal to 0. K is equal to 1, K is equal to 2, K is equal to 3. All the way as you keep on increasing K, the roots, the roots takes, as K increases, the position of the pole takes this continuous line. If you join these lines, it becomes a locus or path of the pole, yes. Now, we study the root locus to see the path in which if you change some parameters, change in parameters, parameters. In the example that we just looked, we had k over s squared plus s plus whatever it was. We found that k otherwise, if k is greater than, then system becomes unstable. This tells us something, that the location of the roots of fruits change with k. Okay. And for this example, at one point, it crosses axis to the right. You have been told it is stable for k up to 9.7. So as you continue, it means for stability, the root must cross to this point. So how does it, what is the trajectory? Or locus? How does it trace from its initial to the final position, depending on change in parameter? We'll only deal with change in gain. But you can deal with any other parameter. So this is topic root locus. How do you know that a point on the S-plane, how do you know that this point is part of the locus, or this point is part of the locus, or this point is the part of the locus? A point on the S is part of the locus if it satisfies magnitude and phase condition. Recall, we are interested only in 1 plus gh of s is equal to 0, which is the characteristic equation, q of s. This means that g of s, gh of s should be equal to -1, and the magnitude means magnitude is equal to 1. -1 is equals to 1 at an angle -180 degrees. When you draw your triangle, -1, and this is j, -j. This is a complex plane, sigma plus j omega. So -1 is equal to 1 at an angle of 180 degrees. So this is the magnitude and phase condition. So are we going to pick all the points on the S-plane, all the infinite points, and test? The answer is no. We are not going to test whether all these points fulfill magnitude and phase conditions. We are not going to do that. We are simply going to apply rules for plotting root locus. So we are going to disregard this, but it's good to understand that you need to test any point. How to get the magnitude? Like if you want to get at this point, is this point part of the locus? If your poles and zeros, you had poles and zeros were located there, this is a graphical method. That GH magnitude is equals to A1, A2, A3 over B1. Is it over B1, B2? Yeah. No, it's the opposite. It should be B over A. However, I'm not going to take this approach. So I'll disregard this, but this is just for understanding. We'll just go straight to the rules. We'll go straight to the rules of the root locus. Number one, the root locus is symmetric about the real axis. This means whatever is on top should be on the bottom. So this should be a mirror. Top, bottom. Number two, as you increase the gain from 0 to infinity, the locus starts from open loop pole and terminates either at a 0 or infinity. So the first thing to do is, if you have your GH, 1 plus GH, characteristic equation. Oh, this is actually a transfer function. It is G over 1 plus GH. It is S plus ZI over S plus PI. So on your plane, you are going to locate position of the roots and poles. So the locus will originate at open loop pole and terminate either at infinity or at a 0. If you have how many poles terminate at infinity? First, let me look for space to write. Poles terminate on zeros. If no zeros, then they are zeros at infinity. That is, if you have one pole, then it will terminate to infinity. How does it terminate to infinity? We are going to look at it shortly. But if there was a 0, then the pole will terminate. If there's a 0 and a pole, it will terminate at a 0. Supposing poles, it means all these poles will terminate at infinity. This will terminate at infinity. This will terminate at infinity. And this will terminate at infinity. The 0 is at infinity. How does it approach infinity? It approaches through some asymptotes. Like if I had one pole, does it go to infinity in that direction, or in that direction, or in that direction, or in that direction? No. We need to get the asymptotes curve. How it goes to infinity, we construct some asymptotes. Now, that is rule. That should be rule number 3. Oh, number 3. I think I have mentioned number 4. Number 3. A point on the real axis lies on the locus if the number of open loops, poles, and zeros to the right of this point is odd. Okay. Suppose you only have real poles and zeros, This on the real axis. A point lies on the locus if and only if the number of poles to the right is equal to 0. So I'll come to this point. Is there poles to the right of, not 0, is if the number of poles or zeros to the right of this point is odd. So if anywhere along this point there is no pole or 0, so it is 0. But when I come here, the number of poles to the right is odd. So this becomes part of the locus. When I come here, the number of, at this point, or rather, let me draw like that. At that point, to the right of this, the number of poles is even. So this is not part of the locus. But when I come here, 1, 2, 3, it is odd. So this becomes part of the locus. So I'll just look at to the right 1, 2, 3, 4. It's even. So yeah, 1, 2, 3, 4, 5, 1, 2. So this part of the locus. Is that. That's the meaning of that rule. That the number of, I see the number of, the sum of poles and zeros on the real axis. So this is the locus. This pole has terminated to a 0. This pole has terminated to a 0. So if I had another pole like here, let me say a pole here, then it means the number here is positive. Then from here, the number is negative. So meaning all the way to infinity. This pole here, every point to the right of this all the way to infinity is part of the axis. Meaning that this pole will terminate at infinity. The branches of the root locus will tend to infinity, do so along straight asymptotes given by this formula. Like, how does it go to infinity? We need to calculate the asymptotes. The asymptotes will cross the real axis at a point known as the centroid, given by sum of real parts of poles minus sum of real parts of zeros minus number of poles, or over number of poles minus number of zeros. I mean, asymptotes must make an angle with the real axis. At one point, because these are asymptotic curves, lines, there is a point here along known as centroid. These asymptotes are basically angles. So they make angles with the real axis, given by this. So once I have my pole arrangement like that, the first thing is that if they're all real, I will say to the right of this is negative, and here. So this will go to infinity. Number two, these two poles must terminate at infinity. First, this pole has terminated to infinity. So these two poles must terminate at infinity. So they will terminate at infinity following some angles called asymptote. But we see that somewhere this pole is coming into that direction and into that direction. So this pole and this pole, this is coming in that direction and this coming into that direction. At one point they'll collide. They'll collide and break away, so that one can go to infinity and the other one can also go to infinity. This point which they collide is referred to as breakaway point. So when you have two poles or two zeros, when you have two zeros on the real axis, the pole will take that direction and this will take this direction. And then it will break away at some point known as breakaway point. How does it go? We are yet to know. And for the zero, we have a pole. If there are only two zeros, then you must be having a pole at infinity joining. This is known as a breaking. Coming into the real axis, and this is breakaway. We still have like 3 more rules. Angle of departure from a complex pole. You have a complex pole here. They occur in conjugates. This pole can either terminate onto a zero or can go to infinity. How does it go to infinity? How does it take off? It depends through some angle. Does it take that angle? Does it take that angle? And then it follows the asymptotes? Does it take that angle and then it follows some asymptotes? No. This angle of departure, this pole, the complex pole, should take a direction, whether that direction or this. When it is either going to find a finite zero, or a zero at infinity. This is known as angle of departure. And it is found from this expression. 180 180 plus sum of angles of vectors to a complex pole in question from other poles, minus plus sum of angles of vectors to a complex pole from other zeros. Let me explain that. Now, you have your pole zero arrangement. This is a pole, this is a pole, they occur in going, these are zero, and these are pole. Angle of departure, how does this pole take off towards the zero or to infinity? It take off from this expression. What you'll do is that you will draw lines from poles to the pole in question. So you're interested in this P. So another one to this, and from zero to this. So this forms an angle theta 1 and theta 2. So 180 minus theta 1 plus theta 2 plus phi 1 angles from other poles from zeros. One 180, which may be plus or minus sum of angles from vectors to other poles, which is this, plus that sum of phi. So if I had another zero again here, I would have called it phi 2. This is a complex pole. How does it take off? The question is, how does it take off? To infinity or to? Yeah. Finally, angle of, similar to angle of takeoff, we have angle of arrival. So if you have a complex zero, and you have a pole, yeah, this if it's one pole. So this will terminate at open loop pole. So one of it will terminate to this point, and another one from infinity will terminate at this. So there'll be one coming from infinity, and there's this one, and somewhere there'll be a break point, which they will break away and then approach this through some angle. Is it through that angle? Is it through this angle? Is it through this angle? This angle is known as angle of arrival. In a similar manner, it is 180 minus sum of phi's plus sum of theta's. Where phi and theta are defined, thetas and phi are defined from this diagram. But now it will be from a zero in question. So this is the angle. Oh. These are the angle. We shall take a few examples. Finally, the loop gain. At any point, you can determine the loop from the magnitude condition, which is the phasor length. This we'll look at an example. If from the locus, actually with the locus, you can determine K at any point. Let's look at some few examples. This is a transfer function. So we do it for K is equal to 1. You know, K will be increased from 0 to infinity. So the locus is for K is equal to 0 at open loop poles. S is equal to 0. S is equal to -1. S is equal to 2. K is equal to infinity. Okay. We proceed. So the first thing, I will draw my S-plane. So from this transfer function, S is equal to 0 has a pole. S is equal to -1 has a pole. And S is equal to -2 has a pole. Let me draw it better. Let me draw it here so that I can have more space. x is equal to 0, -1, -2, sigma j omega. Now, we will go through all the rules one by one. Rule number 1, it is symmetric. Number 2, the first thing I'll have to open loopholes. So rule number 1 says it is symmetric. So that one will come to it later. We confirm. Rule number 1, it is symmetric. Number 2, the locus starts from k is equal to 0 at the open loop poles and will terminate at either 0 or infinity when k is equal to infinity. So that one we are going to determine that in the drawing. Number 3, a point on the real axis lies is part of the locus if the number of the open loop poles and zeros to the right is odd. So we implement number 3. Number 3. Here. I come to this point. Is it odd? Yes, I say it is odd. So the number is odd from this point, like this. And the number is odd all the way to infinity. So meaning this goes to infinity. So we expect that there will be these two bulls will fight here and separate. These two poles will meet, fight and separate. How? And where will they separate? Let's go to rule number 4. Rule number 4. The branches of the root locus will tend to infinity at 2k plus 1, 180, n minus m. Number of poles minus number of zeros. 2k plus 1, 180, n minus m. So asymptotes. 2k plus 1, 180, n minus 1. Okay. Blue. So, how many poles? N minus m. N is equal to 3. There are no zeros. M is equal to 0. So n minus m is equal to 3. We need 3 asymptotes. Because these are branches terminating to infinity. Number of poles times number of zeros. If there are no zeros, then it means all these will terminate at infinity. So for n is equal to 3, we need 3 angles. Two, so k 0, 1, 2. So 2 times 0 plus 1 over 3 times 180. So these are 0 is equal to 60 degrees. Plus or minus, but I can just take the positive. For k, this k is equal to 0. K is equal to 1, 2.1 plus 1 over 3, 180. 3 over 3. And k is equal to 2, 2.2, which is 4 plus 1, 5 over 3 times 180. 300. So this locus will take off to infinity using these three angles, 300 degrees, 180 degrees. No, this is not 180. This is 180. Yeah, 180 degrees, 360 degrees. It's okay. Now, these are asymptotes. They must originate from centroid. Asymptotes must originate from centroid. Let's go to, this was rule number 4. Let's go to rule number 5. The asymptotes must cross the real axis. Sum of real parts of poles minus sum of real parts of zeros over n minus m. Our zeros are nil. Poles 0, -1, -2. So sum of real parts is equal to -1 plus -2 minus, there are no zeros, zeros. Sum of real parts of zeros is 0 over 3 is equal to -1. So our centroid, rule number 5, centroid is -1. Sum of real poles was -2 and -1. There are no zeros. N minus m was 3. So -3 over 3 is -1. Now, this is -1. Our asymptote should start from here. So 60 degrees. 60 degrees is somewhere there. (180 degrees). This is 180 degrees. And 300 degrees. 300 is just -60, yeah? So we have already seen that one locus is going to infinity through this asymptote. You see, this is an asymptote at -180 degrees. Now, the next is that we expect that these two, they will meet and collide and break away and go to infinity at this point. We expect. So let's go to the next rule. Rule number 6, breakaway point. Dk over ds is equal to 0. Dk over ds is equal to 0. So let's write our k over s squared plus 3s plus 2. So I can simply simplify this to be s over s cubed there. S cubed, this s cubed. S cubed plus 3s squared plus 2s. And then once I close the loop, it becomes g over gh, 1 plus gh. And by now, we know that if I close the loop, it becomes this over 1 plus this. Then it is s cubed plus right. So it becomes this over 1 plus this. So, and then if I multiply by the denominator, it becomes k over s cubed plus 3s squared plus 2s plus k. Close loop. This is g over 1 plus gh. And k, so characteristic equation, s cubed plus 3s squared plus 2s plus k is equal to 0, and k is equal to minus s cubed minus 3s squared minus 2s. dq over ds, I differentiate this, it becomes minus 3s squared, 3s squared minus 6 minus 2 is equal to 0. So solve for the roots. 3s squared plus 6s plus 2 is equal to 0. Using minus b plus or minus b squared minus 4ac over 2a under roots. This will give me two roots. It will give me s is equal to negative 0.42 and s is equal to minus 1.574. Minus 1.5 and minus 0.42. I'm only interested in the solution which is between 0 and minus 1. So it must be 0.42. So it must be 0.42. So 0.42 is somewhere around here. So this will break away that way. Now, will it take that path or will it take the out or the inner one? I need to check where it is crossing. Here. I will check where it is crossing shortly, but let's go back to the rules. Yes, we have number 4, we have said asymptotes. We have calculated the asymptotes. Number 5, we have gotten the centroid. Number 6, breakaway point, you have sought. Number 7, we don't have poles on the complex. We don't have complex poles. So this one is not applicable. No complex poles and no complex zeros. Now, intersection. I jumped this rule number 8. Intersection of the root locus branches with imaginary axis is determined from the root criterion. Now, I need to get k. I need to get k at this point using the root locus. So my characteristic question is s cubed, 3s squared, 2sk. So I'll say s cubed, s squared, s and z s power 0. So 1, 3. So we now know 1, 3 and 2k. K. 6 minus k over 3. 6 minus k over 3. And this is 0. And this k will come here. K. So k should be equal to 0. And 6 minus k over 3 should be greater than 0. Meaning 6 minus k should be greater than 0, or 6 should be greater than k, or k should be less than 6. So that all this becomes positive. So worst case, k is equal to 6. So from this equation, s cubed plus 3s squared plus 2s plus k is equal to 0. Solve this. It is difficult to solve because it's order 3, but if we replace js is equal to j omega and then group real terms and negative and the real terms and imaginary terms, this becomes j omega plus 2 j omega is equal to 0, imaginary terms. K is equal to 6. Real terms, 3 j omega squared plus 6 is equal to 0. This basically says minus omega squared, this one, plus 2 is equal to 0. Or omega is squared is equal to 2. Omega is equal to plus or minus root 2 is equal to plus or minus 1.414. This is imaginary. I will have solved also the real. 3 omega squared with a negative. This because of the negative, because of the j, plus 6 is equal to 0. Real part. Or simply minus omega squared is equal to 2. Yielding the same. So to solve this, I've just expressed s is equal to j omega, equate real parts. You get omega plus or minus 1.414. Or imaginary parts. You get the same solution. Now you know that it crosses at 1.414, negative and positive. So I'll now come here, 1.414. And now I'll draw my locus. This is 0.42. 0.42. Yeah. And then I'll draw that. And then as it goes to infinity, it approaches these asymptotes. And this is our solution for the root locus. In summary, rule number 1, we said it is symmetric along this, which is okay. I started by doing s is equal to 0, s is equal to -1, s is equal to -2. We said it will start at this point and terminate at infinity or at finite 0. So rule number 2 is satisfied. Rule number 3, any points to the right should be odd. If every point to the right is odd, then we have that part of the locus. And also this, any point to the right all the way to negative infinity. Rule number 4, asymptotes. Two k plus 1, 180 over n minus m. You go to 180 degrees, 60 degrees, 300 degrees. This is 60 degrees. This 300, which is minus 60. And this is 180 degrees. We say these asymptotes take off the real axis from the centroid. The sum of real parts of poles minus sum of real parts of zeros over number of poles minus number of zeros. And we got was equal to -1. So we came here -1. This is now where we do our 60 degrees, 180 degrees, 300 degrees, and 180 degrees. We saw that between these two poles, despite the fact that they approach each other, they have to go to infinity. So they must break away from this point. So I got QS is equal to 0 and got K is equal to a polynomial and then got the K over ds. I got several solutions and I chose the solution which satisfies this range. Now, having drawn, now I knew that my locus, this will break and will approach infinity using through this locus, through this asymptotes. And now I have to calculate this point so that I know where it crosses. Sometimes it may have crossed on this point depending on the characteristic equation. So I calculated this by dk over ds, by root array. On the verge of instability. This is the point of the verge of instability because the locus. So this problem does again, the system becomes unstable. Now, finally, rule number 9. It says the gain at any point is the product of the phasor length from that point to open loop poles and over phasor length from that point to open loop zeros. Now, what is the gain at this point? K. At this point, K, if you want to calculate K at this point, I will simply do this. A1, A2, A3. So K at any point on the locus can be determined graphically. This arises from the analytical solution. Let's say at this point, for example, let me just repeat that for the sake of at this point, this S naught, and this is S1, S2, S3. This distance, this vector distance, is S naught minus S1. This vector distance is S naught minus S2. And this vector distance is S naught minus S3. So at any point, you can get the gain. And if we had poles, it will have been S naught minus Z1, minus P1, if we had poles. But for this case, we don't have poles. For this case, we don't have poles. Now, I gave you this textbook by Posa. You have this textbook by Posa, not Posa, but Katsuhiko Ogata. I want to go to Root Locus. Yeah. This is basically what you have been discussing. Now, I just want this is what you have in the notes. This is the example that you have in the notes that you have been discussing today. All this, you can refer to this. This is what you have in the notes. So you can look at this page 270 something on this textbook for more. Yeah. These are asymptotes. Now, I just wanted to just give you an idea of add locus. This was just an example. A simple example. Let's look at others. Yes. Let's look at this. This is, which question is this? Okay. S plus 2. S squared plus 2S plus 3. S plus 2 over S squared plus 2S plus 3. What is, this is minus B minus 2 plus or minus square root of B squared minus 4AC. This B squared is 4 minus 4AC is 12, minus 12 over 2A over 2, which is equal to minus 1 plus or minus J. 4 minus 12 is 8. 8. 2 root 2. 2 root 2 is 2 times 1.414. 2.8. So this can be written as S plus 2 over S plus 1 plus J 2.8 S minus 1 S plus 1 minus J 2.8. I'll plot this way. So there'll be a pole at S is equal to 2. There'll be a pole at 0. There'll be a 0 at S is equal to 2. And there'll be a pole at minus 1 plus J root 2. Is it J root 2 or once I divide by 2, root 8 to root 2. So if I divide 2, which is 1.4. So that it comes 1.4 because there's division by 2. 1.4, 1.4. Now, the first rule says to the left of this, the first rule says it has to be symmetric. Symmetric. Number 2, Number 2 originates at open loop to infinity. Number 3, I don't know what was the rule, but centroid, asymptotes. 4 centroid asymptotes. No, the number 3 is says that this is part of the locus. This part of the locus. Number 4, asymptotes. And number 5, centroid. So asymptote is because you have 2 poles and 1, 0, n minus m is equal to 1. So we only have one asymptote, which is 2k plus 1, 180 over 1, n minus m is equal to 1, which is when k is equal to 0, asymptote is equal to 180 degrees. So there's only one branch going to infinity. Centroid, this asymptote will start at centroid. Real part of is minus 1. So real zeros, s is equal to minus 2 zeros. S is equal to minus 1 plus or minus root 2 wholes. Real part of zeros is equal to minus 2. Real part of poles is equal to minus 1. So centroid is equal to minus 1 minus 1 minus 2 over 1 over n minus m 0. So this asymptote just starts at here, going to, but yeah, it just starts at the origin, but this is not the locus. What I've drawn here is the locus. Sorry. This is the locus. Because the number of to the right is, now we have a complex pole here. We have a complex pole, yes. So this pole will take off at an angle, and we'll have a breaking point. We need to have a breaking point here. So one will terminate at a 0, and the other will terminate at infinity. So this will take off through some angle and then come join. This will also take off, come join. How this angle? 180 minus thetas plus zeros plus phi's. So for this angle in question, if I draw this line from 0, you see this line? This angle is 90 degrees. This angle is 90 degrees. And this is -2, -1. So if I join this is 45 degrees. 45 degrees. So this is 180 minus the sum. It's only one pole in question, because if I join minus 90 plus 45 is equal to 135. So if I draw like this, I'll draw 135. 135 is that direction. So this will take off at that angle of 135. check off at that, and this also will check off at negative 135. So if I draw this, it will be negative 135. And I'll have my breaking point somewhere here. So angle of departure is 90 plus, I thought it's 45. Yeah, should be 135 or 145. It is 55. Oh, this is not 1, this is root 2. So this is root 2. Root 2, and this is 1. So the angle is not 45 degrees. This is 1.414. So the angle is not 4. If it was 1, it is 4. So it is 55. So sorry for that. But that was, the angle is 145. I thought this was 1. So this angle cannot be 45 degrees. It's 55. But that's basically how we go about it. Now, I will keep on writing. This is at 2. This is, so this part of the locus to infinity. You have said now this is 145 and this is negative 145. So it will take off using that angle and then it will join at breaking point. Breaking point, decay over ds is equal to 0. Breaking point. I'm just guiding you through. I'm not actually calculating, but I'm just guiding you through. So decay over ds is here. So you will choose one of the s's. Note that this point is part of the root locus, negative 3. It says that this point, negative 3, is somewhere here. The actual breaking point is S is equal to this. Oh yeah, this 0.2, we have negative 2. The point is 0.2 is off. This is negative 2. 0.2 is somewhere here, and it is not part of the locus. Not part of the locus. 0.2 is not part. So the breaking point is negative 3.7. So that you get to decay over ds, you get 3.7. And then now we sketch. We have gotten an angle 45 degrees, negative 3.7. And we said to the right was locus. So this will come and then come, take off. The other one will come this direction and terminate. So this will terminate at 0 at infinity. This will terminate at finite 0. That's how you apply angles of departure. So we said locate. Let's look at one more example. If we have one more example here. These are the rules, locate. I've given you all these rules. All these rules, you have them. I wanted one more example. It's a bit complex, But anyway, you see like this, for example, you have a pole here. You have a 0 here. You have a pole here. You have a pole here. And 2 poles here, for example. So the first thing is that to the right, this is part of the locus and this part of the locus. So you expect that there'll be a breakaway point somewhere in between here, and you'll expect that there'll be a break-in point or breakaway point somewhere here. So these two locus, one will terminate at this finite 0, the other one will terminate at negative infinity. We also have locus. We should have also gotten the asymptotes. Most likely the asymptotes will have been like that, because number of poles minus m is equal to 3. This is 1, 2, 3, 4. 4 minus 1 is equal to 3. So asymptotes will be 30, 300, 60, 180. Yeah. This will terminate at infinity, so I don't know that they'll cross. But you should be able to sketch even without the actual calculation. Just by applying the rules, you should be able to sketch the root locus. Another final example. Yeah. Let's look at this. Once you have this, you know, to the right is odd, to the right is odd, and to the right is odd. Yeah, we expect a breakaway point here, and then it will take some asymptotes to infinity. Number 2, you see these are 3 poles. They will all go to infinity. How will they go to infinity? Asymptotes. Because n minus m is equal to 3, the angles remain 300, 60, 180. So 180 should be there. There should be some centroid somewhere. So the centroid should do something like that. And then angle of takeoff, you see, it doesn't go straight. It takes off at some angle first. It goes through and then it turns like that. It comes and then it turns like that. So basically, just by observation, you can apply rules of root locus. This is just what you have just seen in a short while. I think you have seen all this. Yeah. So I think with that, I will want to end today's session, because now we have cleared the root locus. But to remember the roots are 10. Number 1 is symmetry. Number 2, origin and termination. From a pole to a 0, or pole to infinity, or from infinity to a 0. This finite. If you have a pole to 0, it's finite, pole to 0. But if you don't have a finite 0, it's a pole to infinity. But if you only have a 0, if you have a 0, then the pole will originate at infinity. You saw like this case, which case? If you have 2 zeros like that, and a pole like that. Let me do this. 2 zeros and a pole like that, for example. Then to the right of this is a locus. To the right of this is a locus, because the right is odd. So you expect a break-in point here, and you expect a breakaway point here. So something like that. I was supposed to look one for originating at infinity. But basically, do practice just by observing, make use of the rules. Rule number 3 was to the right of real parts of real axis. If it's to the right of real part axis, it's part of the locus. This is what I'm saying, part of the locus. Number 4 is centroid. Centroid and asymptotes go together. Asymptotes. Now, immediately, centroid and asymptotes, you have a breakaway point. Breakaway point. After the breakaway point, you have angle of departure for complex angles of departure or arrival. Arrival. complex poles and zeros Number 8, we had K. Use roots array. At the point at which the locus is crossing, for locus crossing J omega axis. And finally 9, you can obtain gain. From the locus graphically. So we are going to end there today, and basically, as I said, this is the main reference book, and this is a chapter which I've gotten these notes from, and you can look at this and familiarize yourself. Be able to know the rules of it, be able to apply them, and even to be able to sketch, even without calculating actually the breakaway point, or without calculating the breakaway point, you should be able to know that there exists a breakaway point between some 2 points on the real axis. So for today, I know it has been a bit intense. If there is any question now, I can receive the questions. Hopefully, probably in the next 2 weeks, I will want to clear with the controller, because now what